Hi all, I hope everyone is doing okay in this crazy time. This is going to be one of two PowerPoints voiced over discussing memory. Both of them are going to be, I'm going to anticipate, about 45 minutes long, but the material in them would have taken up 2 full class periods. So it will be quite dense and move relatively quickly. So I hope, because you're watching this from home, you'll take the opportunity to stop and replay and do what you need to do in order to understand. So we're going to start by talking about the different types of memory. The first type of memory is declarative, and that is sometimes referred to as explicit memory. We are going to spend the vast majority of time on declarative memory in this presentation because it is the type of memory that people most often think of as learning, and it includes semantic memory, which is the memory of facts, when your mother's birthday is, for example, or your anniversary date. And in addition, it includes episodic memory, and episodic memory is memory of various events, like the summer you spent at the beach last year or your wedding day. Declarative memory is easily learned, but also easily forgotten. Memory of facts seems to peak around the age of 60. So this is typically because people believe that we older people have experienced a lot of things and those facts build up, and we can draw upon them then later in life to solve problems. Non-declarative memory is sometimes referred to as adaptation to your environment, and I'll give you a few examples to see how that is true. Non-declarative memory is sometimes referred to as implicit memory because once you have learned it, it is much more difficult to forget. Although it does require repetition and practice in order to learn. So one example of non-declarative memory would, for example, be learning how to ride a bike. There are two types of non-declarative memory. The first of those is associative memory. And associative memory is where a behavior is learned because it is rewarded or punished. So examples of this, the prime example of associative memory is classical conditioning, and we've likely heard of Pavlov's dogs, where a tone was associated with food coming. So that's classical conditioning, but in addition, I've added instrumental memory as an example of associative, where, for example, a rat might use some sort of paddle to push in order for food to be delivered, or maybe pushing a paddle so that some sort of electric shock could be avoided. So that's instrumental association. Non-associative learning is learning where there is no inherent reward or punishment. So this does not mean that you don't derive self-satisfaction, but there's no food or there's no electric shock. These are referred to as skills or habits. And there are two general types of non-associative learning. They include habituation and sensitization. So habituation is where, after repeated exposures to some sort of stimulus, you become, I'll say, desensitized to it, meaning that your level of response decreases over time. So an example of this might be if you move to New York City and you hear sirens, or you happen to have an apartment next to train tracks. The first few times you hear those noises, you're going to be very responsive to them. But after about the 4th week of that happening every day, you simply ignore it from then on out. That's habituation. Sensitization is the reverse of that, in that or the opposite of that, in that you hear a response, or you hear some sort of noise and you respond to it, but after a period of time, you become hypersensitive to that noise. And an example of that might be you're hiking in the forest and you hear twigs break behind you, and that happens all of the time. But where the little arrow is on this graph, maybe you turned around and there happened to be a bear behind you. So after that, every time you hear a twig break behind you when you're hiking in the woods, you're going to be very sensitive to that sound. So these non-associative skills and habits are the skills and habits that kept us alive back in the day. Something about declarative memory that I simply find interesting, and I'm just going to throw it out there. People don't really know why this happens. There are a few theories, but there is such a thing as childhood amnesia. And when we think back to our early childhood, we might wonder, why don't we remember being a baby? And in fact, and this is a very old paper, but when individuals were asked about their childhood memories, it seemed that very few individuals had any memory whatsoever before the age of 4. And in fact, articles vary on when childhood amnesia sort of kicks in, but it ranges anywhere from the age of 4 to the age of 8, where some individuals don't remember anything really before the age of 8, and others can remember a few things from the age of 4. It's very difficult to discern because oftentimes our families are telling us stories about what happened when we were babies, and they become sort of ingrained in our minds, and we believe that we actually remember them, but so it's very hard to distinguish to differentiate between things we actually remember and things we were told have happened. But while memory, at least of sounds, things that can startle infants, they actually are learned, and individual or babies or toddlers who are 3 years old can actually remember things that happened to them when they were 2. Certainly, nowadays, even 3 and 4-year-olds remember how to use phones. They know where things are located in the house, so they clearly have those memories, but they tend to get wiped out at some point between, like I said, the ages of 4 and 8. And so the one theory for that is that your brain is still developing at a very rapid rate in that period of time, and the connections are being reformed. And it's possible that the connections that created memories ultimately were redistributed to other locations, and therefore that memory is wiped out. Even though we're going to spend the vast majority of time talking about declarative memory, I just want to take a couple of slides to talk about non-declarative memory, because it is located, or we need different parts of our brains in order to gain non-declarative memory. So non-declarative memory, specifically non-associative memory, is associated with the basal ganglia in the brain, and specifically associated with the striatum. The striatum includes the caudate nucleus and the putamen, and we know this because animal studies, and I have a picture of a radial arm maze there. The mouse or the rat would be put in the middle, and it would learn because of lighting down various paths, or because of some tones that are sounded. It would learn which arms contain, or which arms are the arms that it's supposed to go down, and it would avoid the other arms, and it would learn that. But if the striatum were severed or injured, mice and rats that have learned this now are unable to recall that information, and they are unable to learn new non-declarative memories with lesions in the striatum. So animal studies have shown us that non-declarative memory requires these portions of the brain. Other studies have solidified that knowledge, and this is a T maze, and you see the mouse or rat on one side, and it is meant to travel, either turn right or turn left down at the end of the T. And the way that it knows which direction to turn, if a tone is played after the mouse starts running, that is low in pitch, the mouse learns that it is supposed to turn right. However, if there is a high pitch sound, it knows that it is meant to turn the other way. Down at the bottom of this slide, you see some images of graphs over time. So there were 9 stages, and in each stage there were about 40 trials. So on the rightmost graph, we're looking at the mouse's striatum, and specifically looking at the number of cells in the striatum that are active or firing at the time. And in this time, it happens to be the start of the mouse running the maze. And you can see that in the early parts of this experiment, of course, the striatum is responding, but as we move through the various stages, in fact, the mouse's striatum is responding to a higher level. The same thing is true in the rightmost graph, looking at the goal. The striatum, cells in the striatum are firing early in the experimentation, but they tend to fire more toward the end of the experiment. So there are increases at both the start and the end of the maze. Now, looking at the turn, the third graph in, we see that the mouse was very hypervigilant, having a lot of cells in the striatum being active early in the experimentation, but over time, it doesn't even think about turning, it simply does it. So, so in other words, the cells in the striatum are just automatically, or the mouse has automatically learned with the tone which direction it is meant to turn, and it doesn't have to spend neural energy on that anymore. So these again are cells of the striatum. So this confirms that the striatum is involved in this non-declarative memory. Now I'll switch to declarative memory, and just a few factoids about declarative memory is that there are environmental impacts on declarative memory, our own ability to remember facts and events. Diet certainly plays a role, and specifically they have found that people who ingest a low-fat, high carbohydrate diet, and by carbs I mean vegetables, and not very high in red meat, these individuals tend to have a more robust declarative memory. Anxiety and stress, and specifically cortisol that's released during those times of anxiety and stress, tends to have a negative impact on our ability to remember facts and events, as do distractions, multitasking, and unfinished business. So if there's something that we have in the back of our minds that says, oh, we have to stop at the grocery store on the way home, or oh, I have to remember to pick up my kids from daycare or whatever, those unfinished tasks tend to be distractions that impact negatively our ability to remember things. Sleep has a positive impact on our ability to remember things, specifically deep sleep. Slow wave sleep helps us retain the short-term memories that we have. Exercise 3 times a week tends to build our memory. And drugs, and there are a lot of data to support benzodiazepines specifically, have a negative impact in our ability to remember. So declarative memory follows this sort of path. There is some sort of sensory information. We're collecting information from our environment, and that information can either enter our working memory or enter our short-term memory. Our working memory is memory that we only hold in our minds for a very short period of time, on the order of seconds, versus our short-term memory, where we will hold that in our memory for a longer period of time, on the order of hours. Short-term memory peaks at the age of around 25, and it begins to measurably decrease the older you get. So you guys are probably at your peak of your short-term memory, and I am well past it. Short-term memories, if they are consolidated, and we'll talk about memory consolidation in a little bit, short-term memories can enter our long-term memories. Working memory can as well, but I'll talk about how that might happen in just a second. So working memory is very short-term memory, and I said it was on the order of seconds. So I want you to look at this number. I'll give you about 10 seconds to remember it. Okay, so how many of you recall that series of, I think it was 12 numbers? Well, some of you may have remembered it by associating the first 4 numbers, 1618, with a year, 1618. And maybe you remember that something about that happened in 1618. So you remember those first 4 numbers, and then the next 3 numbers, you knew that there were 922 people who died in a plague in 1618 or something like that. So you might have associated the numbers in that series with something you already know so that you can retain it. Others of you might have chunked the numbers and recognized that series of numbers as a phone number, making it easier to remember. Typically, working memory allows us to remember a series of 7 numbers. Working memory necessitates that we repeat the number or whatever it is that we're trying to hold in our minds. So for example, if somebody is giving us a phone number over the phone and we don't have an opportunity to write it down, we might in our minds continually repeat it. 618-277-9830, 618-277-9830, until we actually dial the number. As I said, not only does it require repetition to hold it in our minds, we also have a limited capacity. Typically, as I said, working memory is about a 7-item list of things. We can memorize, let's say, longer chains of numbers if we chunk them, as I have shown you here with, so you can remember the area code, and then you remember the prefix, and then you remember the 4-digit number at the end. I know I have memorized my credit card number, which is a 15 or 16-digit number, simply by that repetition, right? But typically limited capacity that can be expanded if we chunk or associate the numbers or items with different things, and then a very short duration, usually 30 seconds or less. Although working memory is very short duration, working memory is necessary for planning and problem solving. An example, as I said, working memory can enter our long-term memory, like my credit card number, or like my childhood phone number, or my street address when I was 4 years old. Those are stuck at 4950 Sumac Lane, right? Or 421-5657. Those were my phone numbers when I was in kindergarten, and my address when I was in kindergarten. And I remember those because of sheer repetition. They have entered my long-term memory. And I think it's quite sad to say that this is also why my credit card number is in my long-term memory, because of repeated use. So you can convert working memory to long-term memory over a lot of repetitions, but most often it's short-term memory, things like what we had for lunch or where we went for dinner. Those are short-term memories, and if we deem them important enough to recall, we will consolidate them into long-term memory. One test that is frequently used to measure working memory is the Wisconsin card sorting test. And I have a YouTube URL here that if you download the PowerPoint, you can simply click on this little, click on this little square, and it will take you, or you could copy and paste the URL. It is in Spanish, but you get the gist of what's going on in the Wisconsin card sorting test. Generally, you start out with a few cards laid on the table initially, and the test subject is given a card or selects a card, and then places that card in one of the 4 piles that were initially there to begin with. And the subject is told whether the card that he or she placed on the pile was placed on the correct pile, saying correct, or if not, then incorrect. And the subject very quickly learns how the cards are being sorted. So for example, in the video and in this little diagram from your book, first the cards are sorted by color, and it does not matter what shape is shown on the cards. So the subject would select a card, and then it would place the card on the appropriately colored stack. But at some point, after appropriately placing some number of cards, the rules change, and the subject will place a yellow card on the yellow stack, and the tester will indicate that that's incorrect. And that confuses the subject, but then the subject said, well, what other ways might I be able to sort these cards? And then the subject would lay the yellow squares on top of the black squares, and would be told by the tester that that was correct. And so then the subject realizes that, oh, the rules changed, so now I have to sort them by a different way, or a different mechanism. So recent information, the new information about the rules comes in, and it's going to influence behaviors. So the prefrontal cortex is very important in working memory, and we know this for a couple of reasons. One of them is from individuals who have had their prefrontal cortex injured. An example is Phineas Gage, who you may have heard of already. He was a railroad worker who unfortunately had a spike enter his brain and created significant damage in his frontal lobe, and that impaired his working memory significantly. Your frontal cortex is also involved in facial recognition. Facial recognition is part of your working memory. In this identity task that your book discusses, the subjects are shown faces on a computer screen, and they are there's some sort of delay, and then they are asked when a new face pops up whether that was one of the faces that was on the original screen. When this identity task was done in an MRI and imaging was done, it was shown that specific regions of the frontal cortex were very active during this identity task. In addition to the blue regions, there were these other sort of green highlighted regions that were also very active in recognizing faces. A similar test using faces, it was the location task, and the location task asked subjects to remember not necessarily the faces that were on the screen, but the places on the screen where the faces had been located. So they look at the faces initially, and then the faces go away, and then a new face pops up, and the subject is asked, is this face where one of the other faces were located? This is spatial recognition, and this is also working memory. And rather than those blue areas lighting up or becoming active during this type of working memory, this red area, in addition to the green areas, were very active in the brain. So, so it seems like, yes, it's the prefrontal cortex that's involved in various types of working memory, but where in the cortex that working memory requires the most activity varies based upon what tasks one is being asked to place in his or her working memory. The lateral intraparietal cortex was also very active in these previous studies, and so this is not the prefrontal cortex, but outside of that region of the brain, there were other areas that were required for this working memory. Whether or not they were actually part of the requirement for working memory, or whether they were part of the eye movements required to assess where the faces were or who the faces were, we don't know. But this was another area that was associated with high activity in those previous working memory tests, and so it may be involved. Okay, I had to take a breather there, so maybe you did too. So we understand what part of the brain is associated with working memory, but the question remains, where are long-term memories stored? So the short answer is everywhere. but it took us some time to figure that out. Two individuals were critical in determining how memories are stored, and they were Carl Lashley and his student Donald Hebb. Lashley did some, I'll say, relatively crude experiments where he was lesioning, he was teaching mice and rats to go down mazes and those sorts of things, and then he would introduce lesions into the brains of those rodents, and then they didn't remember what they had learned previously. So you know, that was great, except for it happened regardless of where he induced the lesion. So he said, well, crap, memories are all over the place. And about 20 or 30 years later, Donald Hebb said, let me see if I can put some nuances to this memory storage idea. And he came up with the idea of engrams. So engrams are where memories are stored, and his hypothesis was that engrams were essentially neural circuits. He called them cell assemblies. And so here is a cell assembly where each of these, the dark dots on the perimeter of that circle are neurons, and they are interconnected with one another. When an individual is exposed to some sort of stimulus, in this case shown a circle, there are a series of neurons that are stimulated, and those neurons are all interconnected to one another, and they, as it says here, reverberate or continue to talk to one another even after the stimulus is removed. So Hebbian modification, it says strengthens the connections, and Hebbian modification would be, for example, being shown the circle over and over and over again. So the connections are strengthened over the course of time. And then his idea was that neurons then become wired together because of the learned association, if you will, the connections between them. They're wired together such that subsequent to having those connections firmly wired together, an individual could be shown only part of a circle. So not all of the neurons fire, but because all of the neurons are interconnected to one another, we recognize this as a circle because all of the neurons in that circuit are going to fire even when only a few of them are stimulated. I hope that makes sense. The medial temporal lobe is required for declarative memory to be moved into long-term memory. And I've sort of expanded the region of the medial temporal lobe that we're going to focus upon. And this includes the hippocampus and the entorhinal cortex and the perirhinal cortex together make up the rhinal sulcus that are adjacent to the hippocampus. We're also going to mention the parahippocampal cortex, and all of these areas are critical for long-term memory storage. We know that they're critical because of one patient, Henry Molaison, otherwise known as HM, actually known as HM for 50 years. His identity was hidden under his initials because a lot of publications were put out, but they didn't want to associate his name with those publications until after he passed away. HM suffered from seizures, and in order to stop the seizures, surgeons removed large portions of his medial temporal lobes bilaterally. And so the images on the left show you a normal brain and then HM's brain after removal of those sections of medial temporal lobes. The surgery was a success in that his seizures stopped. However, Henry's life was forever changed because Henry developed amnesia. So most of what Henry lost was his anterograde memory. He was unable to form new memories. He did lose some of his retrograde memories, so things that happened in the past. So there was some evidence of retrograde amnesia, but what was very apparent was his inability to form new declarative memories. He was still able to find his way around his house or to play the piano and draw things. So his non-declarative memory was not as deeply affected. So it seems that the path to long-term memory formation starts with that sensory information that comes into some area of our brain. So whether it's tactile sensation or visual sensation or experiential sensation, that information comes into our cortex, and it then moves through neurons to our parahippocampal and rhinocortical areas and ultimately to the hippocampus. And then the hippocampus is connected back to our prefrontal cortex where long-term memories are thought to be stored. So this is memory consolidation. It is true that the hippocampus has connections to the thalamus and the hypothalamus, and those go through the fornix. These seem to be required for recall because in the absence, or if we ablate the fornix, we have a difficult time recalling some of those memories. So memory consolidation, again, is you have a sensory experience, it enters your short-term memory, and then it somehow is consolidated to become a long-term memory. And so the question is, how does this occur? There are two theories of how we store memory. So on the right-hand side, in the upper right-hand side, we see that there's the cortical regions that are shown in yellow, and there's a single neuron in each of three cortical regions that are getting some sort of stimulus, so that information is coming in, and that information through connections with the parahippocampal region ultimately make their way to the hippocampus. So this is how we make a memory. And then that memory consolidation, the storing of the memory, there are two theories. And the first theory is what's called the standard model. And that standard model is that eventually the connections from the hippocampus back to the cortex can go away. And it's simply the connections between cortical neurons that form that engram that Hebb was talking about. But the question remained, like, how long does this take? Because is it 24 hours later? Is it a week later? Is it a year later? How long does it take for these connections between the hippocampus back to the cortex for those to become not as important anymore? So while there are a few that still believe, still buy into the standard model, a more recent, I guess, model of memory consolidation is called the multiple trace model. And you'll notice that the connections between the hippocampus and the cortex never go away. The green connections, so the connections from the hippocampus back to the cortex, are when the memory is consolidated the first time, but then a memory is recalled, and maybe it is recalled in a different setting, in a different situation, and so it's not exactly the same connections that are made, but some of them do overlap. So each time a memory is revisited, it creates a new trace, thus the multiple traces. If there are many, many traces that overlap, that is thought to solidify or at least make very firm a memory in long-term memory. So recalled memories take different paths, and some of those paths overlap, and that's what allows us to solidify long-term memories. I don't want you to memorize or get all of the details from this slide, but I do want to point out that every time we recall a memory, that brings it back from the long-term memory into short-term memory, and there is potential then to modify that, that memory that had been in our long-term memory. So we're sort of stealing it back from long-term memory and putting it into short-term memory, and it needs to be reconsolidated into a long-term memory. And each time we do that, it makes that short-term memory susceptible to what I say here is interference. It could be solidified, or it could be erased. And so these graphs come from a paper where mice were taught to like plain water rather than sugar water. So they had a preference for plain water. And that is shown in that panel C, where that memory was consolidated. So they have a higher preference, as measured by intake on the y-axis, of plain water, shown in the gray bars, over sugar water, that is shown in the hatched bars. In panel D compared to panel C, that memory, that information of not liking sugar water was recalled, and the mice were given a drug called propranolol. Propranolol is an inhibitor of norepinephrine communication. And when you inhibited norepinephrine's ability to serve as a neurotransmitter, the mice sort of forgot that they didn't like sugar water. And there was the same mice, there was no significant difference between the amount of water that the mice drank versus the amount of sugar water that the mice drank. They simply forgot that they didn't like sugar water, because that long-term memory of not liking sugar water was sort of brought back to short-term memory, and propranolol, giving that drug, inhibiting norepinephrine, prevented the reconsolidation of that memory that had been removed from long-term back to short-term. So it seems that norepinephrine is critical for that consolidation. This is interesting because, not because we care whether mice drink water or sugar water, but this is currently being used to treat PTSD in individuals. So what happens is an individual is asked to recall his or her traumatic experience in a controlled setting, and then when that traumatic experience is brought from long-term memory to short-term memory, the patients are given propranolol, and the memory is reconsolidated, but it's reconsolidated in a now not traumatic setting. So it sort of helps people with PTSD overcome their traumatic experience to some degree. Okay, so spatial memory. Spatial memory is a form of long-term memory. It also requires the medial temporal lobe, and we know that from animal studies. I have a Morris water maze shown on the left, where a rat or a mouse who don't like water or don't like swimming at all learn where a platform is under some cloudy water, so they can't see the platform, but they just learn where it is located in space. In the case of the radial arm maze, they learn which arms might have food. Okay, so they learn where in space certain things are, and damage to the medial temporal lobe prevents animals from gaining this spatial memory. It turns out that the hippocampus and the entorhinal cortex are critical for this spatial memory. And there are specific types of cells located in the hippocampus and the entorhinal cortex that allow for spatial memory. The three different types of cells that I have identified here are place cells located in the hippocampus, and grid and border cells located in the entorhinal cortex. What happens with place cells, so the black lines in each of these images are meant to indicate, so the mouse or the rat that's moving around within a square space. In place cells, every time the mouse crosses an area in this square box, let's say, certain cells, place cells in the hippocampus, fire. So the red indicates the firing of these hippocampal place cells. Grid cells are very similar in that they fire, but they fire when the rat is here or here or here. So the rat can be in any place, and there seems like any place on a grid, and the grid cells then will fire irrespective of where in this box the rat is. But the point is that the rat has to be within some sort of spot along this grid for the entorhinal grid cells to fire. In addition to the grid cells, there are also border cells. So every time the rat comes in contact with some sort of border, the border of the box that he's in, or in this case, there was a wall placed in the box, so that every time the rodent contacted this edge or this wall, border cells would fire. So the combination of these place cells, grid cells, and border cells are thought to provide us with a sense of where we are in place and in space, and it helps us navigate our worlds, right? And so you read in the book the story of the London taxi drivers who had enlarged hippocampal areas as a result of sort of having a really good handle on the map of London, so to speak. That's because you're using your hippocampus to sort of navigate the world. There are individuals that have a very rare condition that's called topographical disorientation, and they are completely unable to navigate their worlds. They get lost in their neighborhoods. In this little diagram here, they even get lost in their house, right? So they just don't have the capacity to know where they are. I read one story where a woman actually had to put pink flamingos in her front yard so she could recognize which house was hers. She also said that it was very difficult to use the GPS navigation in her car and when she was driving around, because it was very confusing, because she didn't know where she was, and this voice was telling her what to do, and that was even more confusing than just getting lost around her neighborhood. It hasn't been, these individuals, because it's very rare, they haven't been studied enough to understand whether this is a problem in their entorhinal cortex or in their hippocampus, but suffice it to say that there are individuals who just get lost.